Hey guys, how are you? Today we are going to discuss an introduction to running time analysis. Runtime analysis, basically earlier we were talking about the Big O annotation and how to find the complexity of an algorithm and all of this stuff. But today we are going to know how to assess the amount of time that this software need to be executed. For that we need to understand a little bit about something called primitive operation, and how much time it takes and how many primitive operations this algorithm takes, and we do summarize of all of these primitive calculations, so we will be able to assess how much time this algorithm will take. But when we talk about the algorithm runtime analysis or algorithm assessment, it's not only about timing. Normally we assess two things. The first thing is the timing, and the other thing is the how much memory or how much storage this algorithm is taking. In our session we are going to look only about the timing, and maybe later or in another session we'll talk about the memory consumption. Okay, so yeah, when we need to analyze an algorithm, we need to check two parts. As I said, the time that this algorithm is taking, and how much memory is going to use to store the data in that algorithm, right? So when we talk about time analysis, we need to know, as I said, how many operation or how many numerical operation, arithmetic operation, comparison, or calling a function, how many primitive operation this algorithm is taking or calculating. And when we talk about primitive operation, basically a summation is a primitive operation, a comparison is a primitive operation, or I'm gonna go through a list of primitive operations that we will consider in our calculation for the runtime analysis. So basically the list of operation includes, but not limited to, the arithmetic operation like addition, multiplication, division, subtraction. This is considered as a primitive operation. Comparing two values is considered a primitive operation. Assigning value to another value like equal, like A is equal B, this is another primitive operation. Indexing of an array, if I say A of I, that means this is another primitive operation. Calling a method, if I call a method in a main, the calling itself is a primitive operation. Returning from a method is a primitive operation. Following an object reference, sending the object by reference, or getting the reference of an object, this is a primitive operation. So okay, this is a more of theoretical part, but let's look about or look at this algorithm. Here I'm saying if I have a function called getMaxArray, basically it has an array and a length of that array. This getMax function, normally it should give me the maximum element in that array. So basically what I should do, I should scan the whole array, and every time I have initial value of the array list, like array of 0, I give it to a temp variable called maxArray, and then every time I scan the array, I'm comparing this value against the values that I have in my hand. If it is greater, then I switch. If it is not, then I continue. So this is basically what this algorithm is doing. I have a parameter called current max. I assign it to the initial element of the array, so A of 0. Now the current max have the maximum, the first element of the array. And then I have another element, which is the length of the array, or the number of iterations that the maximum number of iterations that this for loop is going to have. So basically n minus 1 if the array, because I am starting from 0, so it will go through n minus 1. And then I'm going to have a for loop for I equal 1 to m. Why I started from 1? Because actually I want to start from a of 1, because I had already an operation that makes the current is equal to a of 0. So I'm going to start from a of 1. Okay? So basically what I'm going to do, I'm comparing. If a of I is less than current max, then I switch. I put the a of I as the current max. And then I increment the counter I, and then going forward for this loop till the end of the array. Then I have the current max that has the last or the maximum number of the array, and then I return current max. And then let's do the fun part here. Okay, so I'm gonna cancel this one. Let's open a Word document to analyze this beside what we have. So we have here, and we have our calculation. So I'm gonna take this whole thing as copy. I put it in the Word document so we can analyze it together. Now look at this one. Okay. When we calculate the maximum number, or the number of iteration, so let me go to the pen here, and yeah. So here I wrote 2. Why it is 2? Basically I have indexing here. This is one operation, and I have assignment. Like I'm gonna have a of 0, put it in the current max. So here I have two operations. One is the array indexing, and the other one is the equal. Okay. And what about this one? Here I have also two things. One is the subtraction n minus 1, and another one is the assigning, which is 2. And then here, how many times I'm gonna do this thing? First of all, why here 1 plus n? This is an interesting part. 1 equal I. So here I have 1. See here, the for I equal 1, so I have 1 here, plus 1 to m. How many times I'm gonna do this comparison? Basically I'm gonna do it from 1 to n minus 1, which means n minus 1 times. So n minus 1 times, right? But again I'm gonna have one more time, okay, which is the one that will get me out of the for loop. So basically I'm for any loop, if I say for I equals 0 to n minus 1, okay, so I'm gonna do this n times to enter the loop, and one more time for the last check that will get me out of the loop. So the for loop basically is the boundaries from 2 plus 1, which is the one that is going to get me out of the loop. So here I have the one of the assignment I equal 1, and n minus 1 time comparison plus the one that I'm gonna have to exit from the loop. So this is gonna go with this. So the total number of this comparison is gonna be 1 plus n for this step only. And then here this is gonna have one comparison, which is this part, less than or equal, less than, and one assignment. So this is two times, two operation, and these two operation I'm gonna do it n minus 1 times, which is the number of times that I'm gonna enter this for loop. So 2 multiplied by n minus 1. So here 2 multiply n minus 1, which is okay. So and here also I'm gonna do n minus 1 time for this f, putting into consideration if this condition is always true. Like if I started with the smallest item in the array, and every item in the array is gonna be greater than mine. So basically I'm assuming in this condition gonna be always true. And here we need to talk about something. My assumption or my calculation is going to have, we are talking about the worst case scenario basically. When the array is like this, for example, okay, here 1 2 3 4 5. So this condition is going to be always true, because 1 is less than 2, 2 is less than 3, 3 is less than 4, 4 is less than 5. So that's why I'm considering that this is always true. So I'm going to do this all the time. So again, if I'm doing it all the time, so I'm going to do it n minus 1, which is the number of times that this for loop is executed, plus 2, which is the assigning the indexing of the array, plus the assignment operation, which is this 2. So I have here 2 n minus 1. And then how many times I'm gonna do incrementing of the array? How many times I'm incrementing the array? Basically it's 2n minus 1. Again, n minus 1 time I'm gonna enter the for loop, and the increment is basically I is something like this, I equal I plus 1. So I have here one operation for the summation and one assignment. So this is this 2. So 2 multiplied by number of iterations, and then the return of the function is one call. So basically if we calculate 2 plus 2 is 2, 2 plus 2 is 4, 4 plus 1 5, 5 minus 1 minus 2 is 3, 3 minus 2 is again 1, 1 minus 2 is minus 1 plus 1. So basically all the constants is gone. So let's count the n. So I have here n plus 2n, 3n plus 4n plus 2n is 5n, 5n plus 2n. So total number of calculation is 7 n's. Okay, so, and as I said, this is not the exact number because there are so many assumptions that I didn't put into consideration, which is basically how many times this if statement is gonna be executed or gonna be true. So this is like the worst case scenario for this algorithm. Okay, let's go back to talk about our assumptions. So now I'm talking about the timing, but what I did is basically counting number of operations. How I'm gonna relate this to timing? So I'm gonna assume if B is the worst case scenario or the slowest operation or the slowest primitive operation. So if this is the case, and A is the fastest primitive operation, so my execution of that algorithm might be between 7n multiplied by A, and the upper boundary is 7n multiplied by B, which is what I wrote here. So my worst case scenario is something between the worst case multiplied by number of operation, the worst timing, if I consider B is the slowest time, like for example B is 5 seconds, the slowest primitive operation is taking 5 seconds. So multiply by 7n, which is the number of operations, so I have 35 n seconds. And here, if a is the fastest one, which is taking, for example, taking 1 second, so basically I'm having like something like, sorry, get the pen. If is b as I said 5, so I have 5 multiplied by 3 is my 7, like 3 5 n seconds. And here, if a is equal 1, so 1 multiplied by 7 n seconds. So my worst case scenario is something between 7n seconds to 39n seconds, greater than t is, sorry, control Z. So my t is something here, which is, I consider t of 7n is the worst case scenario. It's between here and here. Okay, so again, if you look at this, it's always parameter constant or linear number multiplied by n here and there. So if I go here, I'm going to talk about the growth rate. The growth rate is basically how I'm going to improve, or how my algorithm getting better. If I increase the speed of the process, instead of having the slowest primitive operation is taking 5 seconds, it took 3, and the highest the fastest one is, instead of taking 1, it took 0.5. So in this case, my algorithm might have a processing time is 0.7, like 3.5 n, which is 7 multiplied by half t of 7n. Okay, and if my fastest operation is getting better by the speed of the processor, and instead of having 5, it become like 3, so it's gonna be 21 n seconds. Okay, so my calculation should be like this, but still it is parameter of n. Okay, and here this is a linear number or a constant or whatever. So I'm gonna talk about something called asymptotic running time. When we talk about asymptomatic running time, we don't take care about the constant or the linear function that is multiplied by me. So my care now is gonna be, if I say my worst case scenario is between x n greater than or equal, sorry, control Z, sorry, here, x n less than or equal my t of n 7n. Okay, and this is less than or equal the fastest one, the slowest one, which is, say, z multiplied by n. So basically my boundary is the n. So if my boundary is the n, I'll go back to the Big O notation, if you can remember, and basically 7n, if you remember, if a function is 7n, so that means it is, if you remember, is zeta of n. I believe if you can review my my video, here is the link, I'm gonna put it in the description of this video, and here you can review the little o and big O annotation, and you will see what asymptomatic means. Basically the boundary of my function. Doesn't matter if I have plus 5 or multiply by 7. I'm talking about the core of the thing, the number of operations. This is the real parameter that I do care about. Okay, so in this case, my big O annotation, I said zeta, I said zeta of n, I said it's gonna be zeta of n, but zeta of n I can consider it as big O of n, which is the most commonly used in our industry. So no one is talking about zeta. People will, for simplicity, will talk about big O annotation. So that's it for this part. But let's talk about some examples and see how we are gonna handle this scenarios. So if we talk about this, for example, this example, I have I have here a for loop. Okay, for loop. In this case, my for loop started from 0 to n minus 1. So how many? First of all, I have the assignment operation, which is I equals 0. This is 1 here, 1. And then how many times I'm gonna do the comparison? Basically, I'm comparing n times, because I start from 0 to n minus 1. This is n time plus the one more comparison that getting me out of the loop. So basically, I have n plus 1 number of comparison. Okay, and how many times I'm comparing? How many times? Sorry, how many times I'm incrementing sorry, how many times I'm doing this operation n minus 1, basically, because here I'm doing two things: the subtraction process plus the comparison process. So the comparison is happening n plus 1 times, because n comparison plus the exit 1, and this subtraction also is happening n minus 1 n plus 1 time. So I have here, this is for the comparison, this is for the comparison, and this is for the subtraction. So I have 1 plus n plus 1 plus n plus 1. And here, how many times I'm gonna do this operation? I'm gonna do it n times, right? N times, because I'm gonna enter the for loop n times. And when I enter the for loop, how many operation I did here? I have assigning or indexing of an array, which is one operation, and then assignment operation, which is a of I equal I. This is an assignment operation. So I have two operations: the assignment and the indexing of the array. So I have this 2n also, and then I'm gonna enter this array, or I'm gonna do this increment n plus 1 times to increment the array. I'm starting from 0 to n minus 1. This is n times, and one more time to exit from the for loop. So it is again n plus 1 operation. So if I count, this is like how many n's? N plus n, 2n plus 4n plus 1, 5n. So 5n is here. 1 plus 1 plus 1, 3 plus 1, 4. So my complexity is 4n plus 4. When we talk about 4n plus 4, we can say for this function 5n plus 4 is what? Is zeta of n. This is what we know, because they are from the same level. If it is zeta of n, for simplicity, people will say it is big O of n. So the for loop, normally the for loop is big O of n. What about the next scenario? If I have nested for loop, here is this is a very interesting example. I have nested for loop. I have for I equal n or equal 0 to n minus 1, and then from j equal 0 to n minus 1. If I have, for example, two-dimensional array, I by n, I by j, so it's gonna be like this. This is the normal operation. Again, 1 for this I equals 0, n plus 1 comparison, because I'm doing the n comparison, plus 1 to exit the for loop, and n plus 1 for the subtraction process, which is here. This is this subtraction process of n minus 1. So I have for the outer for loop this much. Then going inside this for loop, I'm gonna do it n times. So I have n times here, multiply by the same thing for j. So I have 1 plus n plus 1 plus n plus 1, multiply by, sorry, oh, sorry. So now another example, which is the nested for loop. If I go through the nested for loop, if I can say, like the first loop, it's gonna take 1 plus n plus 1 plus n plus 1. Again, this one is the assignment operation, I equals 0, and n plus 1, basically n number of comparison plus 1 iteration to get out of the for loop, and again n number of subtraction plus 1 more for the exit of the loop. So we have n plus 1 plus 1 plus this one, and here is the interesting part. Inside this outer for loop, there is another inner for loop, and this inner for loop is gonna happen n times, because I'm gonna enter this for loop, the bigger one, n times. So I have n multiplied by the same thing, 1 plus n plus 1 plus n plus 1. So I have here n multiplied by all of this. And when I come to this operation, I have two assignment, two indexing plus one assignment, which is 3 multiplied by, here it's n again, and inside this is another n, so n multiplied by n, which is n squared. And then I'm gonna increment the j index for n plus 1, multiply n, because I'm n times from the outer for loop, and from the inner for loop n plus 1. So basically I have here n squared plus 1, and the outer for loop increment is gonna be n plus 1. If we look at this, we will have zeta n square, because I don't care about how many constant or how many constant I add or multiply. The maximum power here is gonna be n plus n square. So this is gonna be zeta n square, which is O, big O of n square. Okay, one more example. If we talk about two successive for loops, the first one will be of type total is going to be, again, like what we said before, 5n plus 4, and the other one is going to be something related to n squared. So if I say I have 5n plus 4 plus something with n squared, so this n squared will win. So in this case it's going to be zeta n squared, and this is negligible because this is already, if I am zeta n squared, that means I am definitely going to be slower than n, or yeah. So this is going to be big O of n squared. So if I have two successive for loops, so the highest power win. So this is going to be n squared, and this is going to give me n. So my algorithm in this case is going to be O of n squared. And the last part we are going to talk about is the if statement. If I have this situation, if I have a for loop, and inside this for loop I have if condition. So basically, I'm not gonna add if else. I'm gonna either do the if or else. I assume the worst scenario. If, for example, this takes 5 in operation, and the else is taking 20 in operation. So I'm gonna use this 20 as the worst case scenario and multiply it by the number of times that this if this is if statement in a for loop. So I'm gonna multiply this by this, but I'm not gonna say my algorithm is gonna be 20n plus 5n, because this is not gonna happen. I cannot have if and else together, either if or else. So I'm gonna take whatever biggest number here or here, and I consider this is the worst case scenario for me. That's it for this session. I hope it was easy for you, and if you need anything related to the Big O Annotation, I will write down the description of the previous video. I hope to go back and review it, and if you need any help or any question, just write it down in the comments. I'll be happy to answer it. If you have any example need me to discuss it in the next session, we can have a session for discussion. Thank you, and I wish you all the best in our algorithm course. See you in the next course. Bye.